Although I am today covering up for yesterday's session, yesterday's question was word ladder. In this question, you are given a dictionary and a beginning word and the end word and some rules. And the rule says that two words are related if they differ by at max one character. So, what you need to do in this question, you need to return the length of the shortest transformation that is possible, starting from the begin word till end word. And in each transformation, you can apply the rules that stated that two words are related if they differ by at least one character, at max one character. So, let's walk through one of the example. You need to start with hit, and you need to check whether you can reach cog or not using the word list, which is acting as a dictionary in this case. How can you reach from hit till cog? This is the explanation given here. Hit, from hit to you go to hot, from hot you go to dot, from dot you go to dog, and from dog you go to cog. How many transactions did we do for reaching the end word? Five transactions. One, two, three, four, five. So actually we did one, two, three, four transactions, and we actually did four transactions, but the total number of words that came in between were five. So transaction plus one gives you the answer. Also, if it is not possible to reach the terminal state, return 0 in those cases. This is a negative case that is being discussed in this example. Without much ado, let's look at the slideshow that I have created. And let me just start the slideshow. This is a typical graph problem. If you are not aware of graphs, don't worry. I'll explain how we can do how can we build graphs, and the second part would be how can we traverse the graphs. In this question, what will we build? We will build an undirected, unweighted graph. What is an undirected graph? Undirected graph means when A and B nodes are connected with each other, there is no specific direction. For example, this one is a directed one. A points to B or B points to A. So there is a particular direction in which the graph flows. In an undirected graph, there is no particular direction. You can either move from A to B or from B to A. What is unweighted? There is no weight assigned on this edge. That means it's an unweighted graph. And I have taken exactly the same example that was specified in the question so as to help you understand better. I will also discuss why we'll go for the BFS reversal or the DFS reversal, whichever is apt. So moving to the next slide now. And let's talk about how are we going to build graph. We will need to define a helper method which tells us whether a string is related to another string or not. So we'll pass the string string A and string B, two strings, to a helper method, and it will return a boolean telling us whether these are related or not. What is the relation between these two strings? That they differ at max by one character. And let's build the graph. The semantics of the graph would be something like this. The first one is the input string, which tells us how many strings are related to this string. The second value is how many strings are related to the string, the key string, and this would be the value where whatever the strings are listed in the value part, these are related to the key string. Let's take an example. Hit and hot, these are related and they differ by one character O. Hot, dot and lot. So this is again a list of strings, dot and lot. Dot differ by dot, hot, dog and lot. There have three words in this part, and so on. So let's break the problem into two parts. As I told, we'll build a helper method that accepts two strings and checks if the two strings differ by at max one character. Pretty simple, and I think everyone would be able to write this code. And how are we going to build the map? We'll iterate over all the elements using two loops and order of n square complexity, and we'll pass for each possibility. We'll invoke the helper method, and we'll build the graph using the response of those helper methods for n into m strings for all the strings. And let's talk about the traversal part. Why we'll go for the BFS and not the DFS one. So in general, for undirected graphs, BFS traversal in this case would give us the answer, and DFS would be time consuming. Let's take an example here. Suppose this is the what we do in a DFS traversal. We traverse over depth, and if from hit you may reach cog in 10 transactions. If the one part could be this, the other part could be a smaller one, which occurs at a depth of 5. So in DFS reversal, what you will be doing is you will be reaching cog, and then you'll be storing that information as a variable, and you'll iterating through all the paths that are present in this graph in a depth DFS fashion. And if you find a better value, then you will replace it with the minimum value. If not, you will continue moving in that traversing the graph. One issue with this would be, since you are moving in depth first, you will be going by one path instead of touching all the boundaries, touching all the nodes that are nearest to the root. That is the case with the BFS reversal, because in BFS reversal we cover edges that are at the same position at the same time. So we go in a breadth-wise fashion. So think of this example, the diagram as a BFS one. So whatever nodes are at a distance 1, we'll consider them first. So you don't need to think of the minimum one part, because minimum will be automatically taken care of by the BFS reversal. So if length is 1 here, distance is 1, this distance is 2, all the nodes at a distance 2 will be traversed at the same time, and for this the distance would be 3. At any point, if you can find your terminal node, you break that condition, that will be the minimum answer, while this is not true with the DFS reversal. Let's move ahead. How are we going to do the BFS reversal in this case? We'll start with an initial word hit, add it into the queue, and we have built this graph by the algorithm that I specified before. And let's move ahead. We added hit, and this is our end word. We pull out the element from the queue, and since it is not equal to end word, we will add all its children that are present in our map into the queue. So this is what we searched for, Hot's children, and we'll add all of them in the queue. So if element is not the end word, which I stated, push all its children in the queue. If they have not been visited in the past, also you need to take care what all children have been visited in the past, so that you don't keep on adding elements again and again. Once all the elements have been pushed, mark that node as visited. Let me just explain the visited concept here. If A is connected with B, and so that means there could be a case where you are pulling out A and adding B's children. Again from B's children you are adding A again. So that generates a cycle kind of a thing. We break the cycle using the visited concept. So let's move ahead in the traversal. So we pulled out hit, we added hot, and we marked hit as visited. Visited gets marked as this, and level gets incremented to 1. And we pull out hot now. Since hot is not equal to cog, what we'll do, we'll add all its children into the queue. So let's add all its children. Dot and lot gets added into the queue, and this tells us the termination of level 2, and this is termination of level 1. So let's move ahead in the traversal. Hot gets added into the visited array. Level increments by 2. This is the terminal state for level 2. And since dot, we pull out dot, and dot is not equal to the end word, we'll add all its children into the queue. Only those children that are not part of the visited array. Since hot is part of the visited array, we'll not add that. We'll add dog and lot. So the dog and lot will go here. So dog and lot gets here, and we just popped out this. Also let's move ahead in the next iteration. We get lot. So lot has hot and dot. Hot and dot are already part of the visited array, so we'll ignore them and move ahead. We'll ignore them. And so next we have dog in the array, and we pull out dog from the queue. We have log and cog as its children. We'll add them in the queue because none of them is visited, and we will move ahead with the iteration. The blue line signifies the end of level 3. So we pulled out dog, and we added dog in the visited array because it has been marked. Let me just take a highlighter here. And let's move ahead with the next lot iteration. Lot has hot and dot. Hot and dot are already part of the visited set. We'll ignore it. And next we have this tells us the termination of level 3. And next in queue is log. We go to log and we see that it's children are dog and cog. We pull out a log from it and add cog to it. So let's move on to the next iteration. Level is 4 so far. Cog, we pulled out cog, and cog turns out to be equal to the terminal word. We found the terminal word and we return level plus 1 as our answer, because I told about transaction plus 1 gives us the accurate answer, and hence level act as the number of transactions that we have done from the root of the graph, root being the start word in this case. So let's quickly code this up. All the elements that are given in our dictionary word. So we will add set, or define a new set, new hash set. And what we are going to do, we'll add all the elements in the hash set that are present in the list. So for integer el in word list, we'll add it in set.add el. And now let's define the helper method that tells us whether two strings are related or not. So the return type of this helper method would be boolean, and let's name strings differ by 1. So we have string A and we have string B, and let's just check whether the length of these strings are equal or not. If a dot length is not equal to b dot length, if they have unequal length, then return false. Otherwise, let's continue with the check. Let's define a boolean variable, found one difference, and initialize it to false for integer I equals to 0. Since both of them have the same length, you can take any of the length, or that of A or B, and let's pull out character, first character from ith character from a string A, and similarly let's pull out the bth character from string B, ith character from string B, and let's check if A char equals to B char. If they are unequal, then let's update found one difference to true. Also, before the check, we need to check whether we have found whether found one difference is already true or not. That means it's a second difference. If that is the case, return false. Otherwise, we'll return true. So this is one of the helper method that tells us whether two strings differ by at max 1 character. And let's define the map. So map is of string comma list of strings. New hash map, and let's build the graph. Let's define a helper method, build graph, and what we'll pass the map to the graph and our data set. Also, we need to add the begin word to the data set, because from the begin word we need to build that graph, not the terminal word. So set.add begin word. if it is there in the word list, it's fine. If it is not, then you have to start the iteration from begin word. Hence, we have added it into our dictionary or the data set of our word list. And let's build a graph. So building graph is also pretty simple exercise. Void, the return type is void, build graph, and what are the two parameters that it is accepting? One is a string, a map, and other one is a set of strings. Sorry, it has to be strings. Word set, and let's build it. For integer I equals to 0, what we can do, we can iterate over the word set array, word set, and a string, and another for loop for string. Let's call inner el word set again. So we are iterating over the string, the array twice using order of n square time complexity, and let's check if el dot equals inner el or not. If they are equal, just continue. Otherwise, let's build the graph, because that means it is the same element. How are we going to build it? We'll check whether they differ by string differs by 1 or not. Then we have el and inner el passed to it. If that is true, then let's add the elements into the graph. So let's get whatever is being stored, map dot get or default el comma new array list, and this will be a list of strings that means connections, and connections dot add inner el. Pretty simple. And let's just put this information back in the map, connections. So what we have done, we have built the graph, we pulled out the information from the map, what all connections already existed, and added the new connection to this, and put the same information back into the map. So since this means that el is connected to inner el, and similarly, what we need to do, we need to establish the connection between inner el to al. So I'll repeat the same process. Connections for inner el, and this time the key would be inner el, and we'll be adding el to it, the element to it, and inner el would be the key again, and this would be connections to connections for inner el, and this is how we have built the graph, and we are successful. And let's define another set which is of strings again, which tells us what all elements have been visited. So visited is very important. Hash set for strings, and this is a visited array. Let's define a queue. We are standard way of writing the VFS traversal: queue new linked list, and queue dot offer. From which word are we starting? Begin word. We are starting from the begin word. And while queue is not empty, let's calculate the size. Queue dot size, and while size minus minus is greater than 0, we'll pull out the head element. Queue dot pull out the head element, and if we check if head equals to the end word. If that is the case, we'll return level plus 1. So let's define variable level and return level plus 1. That's good. And let's check if visited dot contains head. If it contains head, just continue with the iteration. Otherwise, if it doesn't contain head, so that means head is an unvisited element, we'll add all its children into the queue. So string all its children means all its connections. Let's call it connection map.get or default. What is the key? Head is the key. And what is the default list? Array list. And let's check if visited does not contain connection. If that connection is not present in visited array, we'll add it in the visited array. Q.offer visited, and let's mark, since all its connections have been added, we'll mark the head as visited dot add head. And once we are done with this logic, we'll check if visited dot contains end word. If that contains end word, we'll return level. Otherwise, we'll return 0. Simple way of checking. If it has the end word, then we return the level. If it doesn't have the end word, we'll return 0. That means it's not present. Also, I forgot to increment the level, so I'll increment it level head. Fingers crossed. It's kind of a verbose code. Compilation error. Again, some typo, sorry for that. Oh, sorry, it has to be connection instead of visited. Absolutely correct. And let me just submit this code. Accepted. This time the solution got accepted. And let's talk about the time complexity. Time complexity of a graph traversal problem is order of n square / order of v plus c, which is number of vertices plus edges. And also you are building the graph in order of n square complexity, hence it is order of n. The worst case would be order of n square. The space complexity would be again order of v plus c, the number of vertices plus edges. Thanks for watching the video.